Hi, and welcome to Dr. V's Chemistry Webcast. In this webcast, we're going to be talking about families of elements, the groups of elements that have similar characteristics, and what you need to know about them. Most of the elements in the periodic table are actually metals. The vast majority of the naturally occurring elements do fall into the blah, blah, blah. Hi, and welcome to Dr. V's Chemistry Webcast. In this webcast, we're going to be talking about families of elements, groups of elements with similar properties. Some of them have names and certain characteristics that chemistry students really need to know. Most of the elements in the periodic table are metals, and then we have the nonmetals, and in between are the metalloids. So let's talk about these and compare their properties very briefly. Metals, for the most part, are found as solids, the exception being mercury, one of only two elements that's a liquid at room temperature. They're lustrous, which means they're shiny. They're good conductors of both heat and electricity. They're malleable, and that means you can hammer them into a thin sheet. And they're also ductile, which means they can be pulled into wires. We're all familiar with copper wire, for example. Our nonmetals may be found as solids, liquids, or gases, so we see a little more variety in states of matter with our nonmetals. The solids, when they are present, tend to be brittle. Think like charcoal. And typically, the nonmetals are non-conductors of heat or electricity. Okay, so it's good to know the differences between these two broad categories. In between them are the metalloids, which have properties of metals and nonmetals. They're on that staircase to heaven, right? There's not always universal agreement about which elements are metalloids, but if they're in that region in between, that interface, they're kind of wannabes. They're not quite metals, they're not quite nonmetals. They have properties of both. They just want to fit in. Let's talk about the group 1 elements, the alkali metals: lithium, sodium, potassium, rubidium, cesium, and francium. Now, I do want to point out that although hydrogen does fit into group 1, it's not considered an alkali metal. It doesn't behave as a metal. It really doesn't have metallic properties. But let's talk about the alkali metals and some of their behaviors. They're the most reactive metals. In fact, they're so reactive, we have to store them under oil. They're not found as free elements in nature. You're not going to go digging around in the backyard and find a lump of potassium. You're only going to find these as compounds. Usually they're salts, sodium chloride, etc. All right. They are very reactive, but they're also very soft metals, and you can cut them with a knife. So in this picture, what we see is that there's an oxide layer that's formed around the outer edge of the sample, and if we cut it away, we can see that shiny metal that's inside. All right. They do react vigorously with water when you add them to water. In fact, as you go from lithium to sodium to potassium to cesium, it gets more and more and more invigorating and more exciting. Like I said, they're shiny and they're silver colored. When we cut away that oxide layer on the outside, we can see that silvery color, and they're very shiny. The other thing that's important for you to know about the alkali metals is that they typically form ions with a 1+ charge by losing one electron. So we'll see lithium ion and sodium ion and potassium ion. They're all +1, and they all fit into group 1. That makes it easy to remember. Okay. Let's go on and talk about the group 2 elements, which are called the alkaline earth metals. So you have to be careful. Group 1 are the alkali metals. Group 2 are the alkaline earth metals. They're less reactive than the alkali metals. Here's a picture of calcium shavings, and see they're silvery and shiny. You know, when we think of calcium, so often people think of calcium containing compounds like eggshells and bones, which are white and solid. But pure calcium is shiny and silvery and malleable. It's a metal. Sometimes people forget that. The other thing I should mention about the group 2 elements is they also are not found as free elements in nature, but only as in compounds. Right? So you'll see magnesium sulfate and things like that, but you're not going to go digging around in the ground and find a chunk of strontium metal. This is a picture of beryllium, which is really, really toxic, so you're not really ever going to see that. The other thing I wanted to mention about the group 2 elements is that they typically form ions with a 2+ charge. Magnesium ion, calcium ion, strontium ion, they're all 2+, and they're in group 2. Well, that's really convenient, and it makes it easy to remember. I've got a picture here of magnesium ribbon, which is a very common form of magnesium, one you might use in lab this year. I know my students certainly will. And is there anything else I need to say about the alkaline earth metals? Nothing comes to mind. The next category that I'd like to talk about are called the transition metals collectively, and these are the elements in groups 3 through 12 of the periodic table. What I want you to know about the transition metals is that their compounds are often intensely colored, so a lot of pigments and paints and inks contain transition metals. In fact, if you see something that's highly colored, you should ask yourself, I wonder if that contains a transition metal element. In fact, the other thing I wanted to mention about transition metals is that they can form several different cations with different charges. So the group 1 elements only do +1, and the group 2 elements only do +2. But the transition metals, many of them can do many ions. So for example, chromium 3 chloride is this intense purple color, but chromium 6 oxide is bright red. And a lot of the other transition metals can also form several cations with these intense colors, and in fact, each ion might have a different color. I wanted to mention hemoglobin, which is a metalloprotein. The deoxyhemoglobin is the one that does not have oxygen. That's in your venous blood, all right, versus the oxyhemoglobin, which contains an oxygen, which is bright red. So we can actually see in hemoglobin the iron atom, whether it has an oxygen or does not have an oxygen, actually changes the color of the compound. So transition metals are everywhere, and I love proteins, so we're good to go. I also will briefly mention the inner transition metals, which are also sometimes called the rare earths, and these are the lanthanides and actinides that are down at the bottom of the table. We're not going to go into much detail with the inner transition metals. They're very similar in a lot of their chemical properties, which made it hard for them to be identified from each other. Many of them are radioactive. They're not necessarily all that rare, and they do have a lot of industrial uses, but we're going to focus on the rest of the periodic table. The next group I want to discuss are called the chalcogens for group 16. So not every group has a special name, but the ones you need to know, you really need to know. They tend to form ions with a -2 charge. So the oxide ion, the sulfide ion, the selenide ion. I've got some pictures of these elements here. So selenium is a grayish solid. Sulfur is a yellow solid. Was found around the mouths of volcanoes. It was often called brimstone. For those of you in your literature classes where they're talking about fire and brimstone. Well, brimstone is sulfur. Oxygen in its natural state is a colorless, odorless gas, but when it's liquefied, as in this picture, it's got a pale blue color. Isn't that interesting? So the group 16 elements, the oxygen family, are referred to as the chalcogens. The group 17 elements are referred to as the halogens. This comes from the term salt former because so many of them are the anions and salt compounds. They're the most reactive nonmetals, right? So they're in group 17, second to last over on the right in terms of what group they're in. Here's a picture of fluorine gas, which is a pale yellow-green gas. Very, very reactive. The other thing you should know about the halogens over in group 17 is they tend to form ions with a -1 charge. So the fluoride ion, the chloride ion, the bromide ion. Here's a picture of bromine liquid and vapor. It's got this characteristic reddish-orange color. It can be a gas at room temperature, but it does also exist as a liquid, and here we can see both of them. The other thing I want you to know about the halogens, and this is very important, is that they're found as diatomic molecules. That's what they exist as in nature. F2, I2, Cl2, Br2, diatomic molecules, 2 atoms of the halogens in the molecules. Here's a picture of iodine vapor, which has this really beautiful purple color, and a picture of chlorine gas, which is a little less yellow than the fluorine. All right, but that's all very good stuff to know. Another thing to mention, I'll just mention this as an aside, all the colored gases are poisonous. If it's a colored gas and it's coming towards you, you better get out of the way. All right, finally, we're going to talk about the group 18 elements, which are referred to as the noble gases. When I was in school, they were still called the inert gases. It was thought they did not make compounds at all. They're non-reactive. They're colorless and odorless gases, and they don't tend to form ions at all. They always stay as neutral atoms. They really don't form compounds. However, we have made, not me personally, but scientists have made some compounds containing the heavier noble gases, xenon and krypton. And so they're not completely unreactive. It's just really, 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 really hard to get them to react and do anything. But you do need to know that the group 18 elements are the noble gases. The other thing, the last thing I wanted to mention, is that there are some elements that exist as diatomic molecules, and chemistry students need to know this. And if no one ever tells you, how would you know? So we talked about the halogens, fluorine, chlorine, iodine, and bromine acting or behaving, existing as diatomic molecules. But we also see this for hydrogen, oxygen, and nitrogen. So if you take your periodic table and shade those in, kind of looks like a 7. There's 7 of them. just as an aside, I'm going to mention that phosphorus exists as 4-atom molecules, P4, and sulfur is often found as 8-atom molecules, S8. So that's worth knowing as well. But the diatomics, you really need to know that when you get into your reaction writing. That's going to be very, very helpful for you to know. So just to wrap things up, each family or group of elements has similar properties, and you need to know the names and the characteristics of the key families. You need to know what group goes to what name, and if they form a typical charge, what they do. So we'll talk another time. I can talk about the periodic table all day long, but we'll stop here.